Hey, we are live and online for the OpenStack Bootstrapping Hour. Welcome, folks. Today we've got myself, Sean Dague. We have Jay. Introduce yourself, Jay. He's waving. We have Dan Smith, who never fails the gate. And we have Matt Riedemann, although we're still working some audio issues. We may or may not hear from him over the course of things. So today, in sort of response to requests that were happening around the Design Summit, we decided to do a session on debugging in the gate. There aren't slides for this, but there is an Etherpad, and the Etherpad is something that jump on. We've got sort of a structured document that we'll go through. And there's a place to add questions at the end of the Etherpad, and we'll answer any questions that show up there as well. So with that, unless Jay, Dan, you guys want to say anything before we get started, or just dive in?
Nope.
Okay.
I'm not doing that.
You're not doing that.
The thing that Jay just did.
Okay. All right, so the Etherpad is up. It is available in the wiki as well, but for people looking for the URL, obh-debugging-openstack-gate. In order to, before we get started about like actually debugging a situation in the gate, we have to kind of understand what this means. The word gate gets thrown around by a lot of people to mean slightly different things at different times, and mostly it's an artifact of the way our system overall works. So we talk about the gate, we're really talking about the fact is that we've got this system for running tests in a pipeline called Zool, based off of the obvious Ghostbusters reference. Within it, there's this concept of pipeline. So when you have a test, when you upload a patch anywhere in OpenStack, we have tests associated with it in various pipelines. And what pipeline means is that we have this thing called a check pipeline where we'll just run whatever tests you want to run on that one patch kind of on its own. But we also want the ability to be able to land patches after testing them into Git trees, ensuring that, because a whole bunch of the OpenStack components are actually quite tightly coupled today, like all of the integrated release and a lot of the libraries, what we want to do is make sure that a patch in one can't break an in-flight patch in the other. And so we've got this thing called dependent pipeline, wherein we might queue up like 20 patches, and they're all running in parallel in this sort of speculative merge model. And if you're more interested in all the mechanics behind this, there's a link that Jay put in here appropriately about how the Zool system works. But the net of it is that the tests on any given patch take about an hour to run. Having this speculative gate pipeline where we can stack a whole bunch of them up means that we can run more than 24 patches in a day. That's supposed to be in a day. So we're not doing them serially, we're kind of doing them in parallel. And there's a whole mechanism that happens, if something fails, the speculation fails. There are presentations around the Zool basic mechanism there. We run all sorts of tests. Today, we are only going to talk about one class of them, which is things that run, bring up a dev stack, bring up the entire environment, all the OpenStack services around it, and run Tempest. Because we talk about unit tests or style checks or whatever failing, replicating those locally is usually pretty simple. Even when it's not simple, at least it's possible, and it's a much more familiar environment to most people. But running the way we run a whole dev stack environment and the Tempest tests around it is a thing that sometimes confuses people a little bit or don't quite realize what's going on. And then so debugging that and getting to the bottom of how or why a failure happened is actually often quite hard, especially if you're not familiar with it. So kind of this third block of text here. We have a whole ton of tests that are running that are these DevStack VM tests. So we start a cloud instance somewhere, we put DevStack on it, we start a whole bunch of services, and then we run Tempest against those services. Tempest has about 2,000 tests in a normal run, and we hit everything kind of all at once, and it should all pass. These are yes, and there's a nice link that was just added that describes even that in a little more detail. When we run Tempest, which is our set of integration tests, we run them in these environments. We run them with 4 workers. So Tempest, using the test repository underlying infrastructure, kind of breaks all its tests up into 4 buckets, does it dynamically, and then has them all happening in parallel.
And that has changed before, right? Wasn't it 3 not too long ago?
It was 2, yeah. So it was 2 for a long time. The way we've got the logic, it was 1 for a long time. The way we've got the logic encoded right now is it runs half as many workers as CPUs in the guest environment. And all of our upstream test nodes have 8 virtual CPUs at this point. So we found that was, if you run the same number of workers as virtual CPUs, especially given the way the worker processes and OpenStack services run, we end up just like being in a CPU peg environment the entire time, and like things fail for other reasons, which maybe or maybe not, they should maybe or maybe not actually fail in those cases, but they fail a lot, and it wasn't worth sorting it out. Running at half the number of workers as CPUs is reasonably reliable. This has some really nice impacts. So while we do build all of the services into a single node and everything's running on the same machine, which is very unlike a real deployment would be, it's a massive simplification of it. The way we run the tests against this environment actually is a little bit more like how a real cloud would work, because it does mean that the API endpoints are getting hit by requests simultaneously by different tenants, which is a thing that you would expect if you were running a real cloud. It does mean that certain, kind of key chunks of work, like booting a guest, by the fact that we're hitting this with 4 workers at once, there very well might be more than one guest being booted at the same time by possibly different tenants or the same tenant. And that, again, is kind of like a real cloud. And all the artifacts that get generated when things both work and fail are only the kinds of artifacts that OpenStack itself generates. So, the log streams, I guess we don't capture all the notifications, but basically, the debugging process for something broke in this cloud is actually quite similar to what you'd be dealing with a production cloud, which means that when OpenStack's debuggability in general is terrible, then debugging gate failures is equally terrible. And one of the things to talk about a little later is, like, sometimes you can't quite figure out what's going on. It's about moving the ball forward as to how would someone in the future be able to figure out what went horribly wrong in this particular case. There are some common so when you push these patches, it might be that your patch fails because our tests fail because your patch actually broke something, and it does catch a lot of those. and that's that's great. That's kind of why the system works. But people will run into situations where they feel that this was probably not because of their patch, or it's actually provably not because of their patch, right? They changed a piece of documentation and they weren't able to boot a guest. And part of what gets people frustrated is like, how is this possible? How could this ever happen? I have a blog post where I went into a particular example of this in quite a lot of detail, and the point was that because in our unit testing environments, or because the only tests that we run regularly besides these Tempest tests where we build all the services together and run real requests on them is a much smaller unit of testing, these unit tests which run very isolated chunks of code. There are very clearly assumptions that get made throughout the OpenStack code base about what global state looks like, that it's synchronized in a way that it actually isn't, or that a chunk of global state doesn't have to be locked because there's no possible way two people might be doing this thing at the same time when they might. This is arguably made more confusing because of our use of eventlet, where sometimes it's not always clear unless you're really knowledgeable in when eventlet decides to use green threads and stop execution on one part and jump to another, that, oh, that piece of code actually could be touched kind of by two green threads, and we need a synchronization mechanism around it. And so for many services, or many just places within OpenStack together, when we run these Tempest tests in this four-worker environment, it's actually the first time we've done testing of hitting an API endpoint with more than one request at the same time. And in almost every case that we've lit a new service into the integrated gate, we have found that the service made some critically bad assumption about some piece of state that meant that if you hit it with two API requests at the same time, it actually fell over. I think almost, I can't remember if we actually hit it with every new service that we've integrated, but we've hit it with most of them. And usually it's something really simple, and you're like, oh yeah, you should deal with this. But that also kind of opens up this question of like, it'd be great if we could find that earlier. So when things go horribly, horribly, horribly wrong, which they do reasonably often, the next question is like, how do you figure out what happened? So once your job reports in, you'll actually get links to the console logs of these environments. And in the console log, I clicked the wrong thing. So in the console log, you'll end up with something that looks. I'm actually gonna maybe. Dan, do you want to click that that console log link? Although you have to delete the last paren off of it. So these things kind of look big and gross and nasty, and if you scroll to the end, you'll see kind of where some of these test failures occurred, and there will be big stack traces the whole way. There's a whole list of Tempest tests happening, and then we get kind of the output in gory detail of all the debug that we captured on the way down, and eventually there'll be a big test failed. Here it is. So just getting a handle on how these consoles look and how to address them is sort of step one, because people will be like, my thing failed. I'm like, okay, let's start. Let's go first and capture the output console and see what's going on. And honestly, there's sort of like, we're going to do a little bit of binary decision making here about, is it this or is it that? Because the first thing you got to figure out is when your job failed, did it fail? Did it actually fail in Tempest, which means that the services are probably up, the setup for the environment probably worked correctly, but we tripped over a race condition, especially if like the number of test fails is like a small integer, like a small integer number. If it failed, like in this case, we failed one test and we passed 528. So this is not like some systemic problem with the environment. This is, we tripped over some race condition. It's pretty targeted, and now we got to figure out like why this failed in this particular environment.
Just to be clear,
yep.
You just said if you see one test fail like this, you hit a race condition. But of course, this can be that you actually broke something legitimate, right?
That's true. So the first step is, are you really, really sure that your patch didn't break this thing? Most of the time, honestly, if it's your patch that broke the thing, it probably will fail more than one test, because we tend to hit parts of the surface multiple times. If it's just one test, the odds are a little higher that it's not. But like, yes, convince yourself that there's not a way that your test might have been responsible for that, or your patch might have been responsible for this. The other thing that might have happened, if you want to jump back to the Etherpad, it's probably good for that, is that. Yep.
Before you do, I wanted to, and sorry if this is out of order, but when I'm looking at this console thing, I mean, there's a ton of data in here, right?
Yeah.
And especially like this one had, like 30 minutes of Tempest barfing that it was trying to do something right. Makes it really hard sometimes to actually tell which test failed sometimes. So I go to this this results HTML.
The tester results?
Yeah, yep. Which makes it much easier to, it's very big and my machine's very busy doing this, but makes it much easier to see the one thing that failed, right, and have a little bit more context around it, because console is just like a ton of stuff, right?
No, absolutely. So that brings up a really good point, is that we provide this information in a couple of different views. Depending on your comfort level, like this might be actually a much better view to go look at the tester results.html, and it will tell you give you this nicer view. It's basically formatting the test repository subunit stream into HTML and like just show you kind of embedded what the failure is. Yep, it's a good point. So it's actually possible you didn't even get this far. It's quite possible that the failure happened well before you ever got to Tempest, which meant there was some setup failure in the environment. And that, again, it could be related to your code. Like you could have broken the ability of one of the services to start, which is not unheard of, happens. It could be something completely outside your control, environmental system, a bad dependency shift. Honestly, when you start down a path, one of the first things to go to figure out like what's going on and is this something new is this link to Logstash here, which actually the blog post that I have above about the Elastic Recheck talk that I gave talks about this in a little more detail. But there's a search engine. We put all the logs that we do, all the logs at info level or above that we capture from all our test runs goes into the system and is full text indexed so that you can find what looks like the indicative failure line, throw it in here, see if it shows up more than once, see if it shows up on somebody else's test run. It's faceted so that you can kind of drill down into the results of like which build was it, which project did this test run on, et cetera, et cetera. We have a system which actually does a ton of this for you automatically, which is called Elastic Recheck, and that's like the other link that's here, where we try to, it's just /recheck now too, I think, where we build sort of tests, appropriate search signatures for log stash for particular bugs that we're well aware of, and then we kind of figure out which ones are the ones that are showing up most often now. Some things become terrible, like this. The thing that's at the top of the list right now, it's ordered by the number of failures in the last 24 hours to keep it kind of relevant. Had to do with a requirement slippage issue, which basically ruined all of stable. Which meant it was this sort of giant number of hits over a short period of time, and basically was blocking everything in those jobs. But some of these other ones are things that happen, a lot less frequently, we've got this issue right now. The next biggest issue has to do with deleting subnets in Neutron, and they're apparently being a timing issue. And this LVM issue has been hanging out for a while now, and that's actually probably one of the bigger ones to go address. So this is current to within an hour, unless the systems get backed up, but we try to keep this pretty current. Okay, so that's sort of the infrastructure around this. We'll actually keep going through this decision tree of how do we make further and further progress on figuring out what happened. The first class of things, we just talked about infrastructure failures. We never got to Tempest. Everything blew up well before that. Then, what's going on? And honestly, the biggest low-hanging fruit that I find here is there was probably a release of a Python library. And so go look to see if there's anything that looks like I can't install this thing, or something exploded in this Python module within the DevStack setup, and go search on PyPy to figure out if there was a new library release. When the test tools break that just happened, was that something's really wrong with all of the testing infrastructure. Okay, test tools subunit, test repository, what released recently? Test tools released yesterday. Was that the issue? Yeah, turned out it was the issue. Matt points out a good point about the Oslo DB. When that released, there are some projects that are still gating on whether or not their config file is what they expect it to be, but because we let libraries modify the config file, that means somebody else's library releasing can actually break your system. And I know at least Heat and some other projects were broken because of that until they got things. Okay, so that's one class of things, and those will happen, and those tend to happen if that happens, you'll see all the jobs everywhere failing because something is deeply wrong. Fortunately, those things tend to be big spikes that we deal with quickly. This other class of things, which is a Tempest test failed, and just one failed, and it just failed this time, and didn't fail last time you uploaded the same patch. What's going on? And think of this as sort of successive waves of understanding. If that, the first thing is figure out what the test is actually doing, right? Tempest is an open source project as well. Go look at it. Here's this test. What does it think it's doing? This is the thing. Surprisingly enough, most people, when they go in and dive to try to figure out what's going on, they don't actually try to figure out what it was supposed to do. Because every once in a while, you also might see that the test itself, expected synchronous action out of an asynchronous activity. And maybe that's the issue. We've gotten most of those, but as APIs change over time, maybe we did or did not get all of them. But also, more importantly, out of reading the actual test, you can figure out what are all the services that are being accessed in this test. It was bringing, was it starting a server, which meant that it's going to be talking to Nova. So if it broke somewhere, the Nova services might be in play. Was it creating a volume, which means it's talking to Cinder? Like, okay, clearly we need to make sure we understand what's going on with Cinder in these cases. Because usually it's not going to be something completely crazy that's happening, like that's unrelated to what this test is. Like, it's got a path, it's doing some things. Other tests might be doing things at the same time, but at least you've now narrowed out of like the 25 services that we're running, we've got maybe 8 daemons we have to go look at to figure out if there's information. Yep.
I'm trying to read ahead and not jump the gun, but I don't see that you say anywhere in here, like, I mean, with volume, it could be Nova or it could be Cinder, depending on whether it's like booting from volume or whatever, right? But if you know that it's like just going to be a Nova thing, you don't say anywhere in here like what to start looking for there. So I was just going to maybe show the some of the service logs.
So at the bottom of the console page, actually scroll all the way to the bottom.
Oh, this. Yeah.
Yeah. So we attempted to. This shows up inside the Apache footers for every single console page. Like, here are all the logs, and these are the logs that relate to these particular services, especially now that, some of these things don't match as well as they should because they had a naming convention which predated us having so many systems, and there was an attempt to do short names for other reasons. That'll actually get cleaned up this cycle, and all the logs should be really descriptive of what service they're working with now. But there is an attempt to both map out all the files that exist so that you kind of know, like, hey, I want to deal with Nova. These are the Nova files. As well as below for the places where we have some common patterns of go through things in this order because this is your most likely sequence of things, of finding a thing that went terribly wrong, to try to do that.
So when I'm debugging usually something that I broke, especially if I get a Tempest test that like throws a 500 or gets a 500 from Nova, that means like something broke, right? Depending on where I made the change, or maybe if I've guessed based on what the test failure is, I go usually because of the things I'm breaking. It's Nova CPU. But if you go into these Nova API, Nova CPU logs here, the first thing I do is load it up and then I hit this trace filter.
Yes.
And then I just scroll here and here, and there's something that I've broken. Okay, so there's a whole bunch of text, right? And that usually is like 3 clicks of really close to actual problems.
Yes. Am I better now, Jay?
No, I'm sorry. I was trying to fix Dan's
feedback loop. Okay, no problem.
I thought maybe it was you, but no.
Okay.
It's Dan.
Okay. So Dan. So to reiterate, Dan brings up this good point. It was sort of like cross reference. So like the last thing before we jump there is that the other thing that's important when you're go through the console log, and this is a reason I'm not sure the test results give you maybe quite as much information. It might be there. Timestamps are important because you're going to want to know about when the failure occurred, so that when you look at these logs, if you see like a horrible explosion in the log somewhere, you don't immediately say, oh, there's a horrible explosion, that was my issue, and it turns out it happened 10 minutes before your issue ever happened, which is very possible. Because the thing that Dan just talked about, which is sort of in this cross-reference the log section, kind of the first thing to do is, okay, this was a Nova failure. Like it was something didn't happen with the compute starting correctly. Okay, so it's got to be a Nova issue. It's going to be in Nova log somewhere. There should be something. And if you go to the logs for that, and then I do the same thing Dan does. First thing you do is you go, we've got across the top, we've got those filters based on log levels. You just hit the trace level. So like all stack traces, warnings, and errors get displayed. Everything else gets hidden. And see if there is a stack trace at approximately the right time based on when things failed. That becomes a high likelihood that that's, that it exploded and that's why everything went wrong.
Yep. How difficult do you think it would be to have a aggregated, sorted by timestamp single log file? Because it does get quite annoying. Well, like once you identify that timestamp, right, that say happened on Nova API or Nova Compute, then especially if you're looking for like timeout issues, then you're either going to like the Cinder volume or the network agents and looking for that particular timestamp, and it can be time-consuming. Would be a good way of describing it.
Sure.
Of switching back and forth between all the different log files. Do you think it's possible that we could get something that was just a single file that was just sorted by timestamp?
So I think that what you'll find if you do that in the naive way is you'll just expose yourself to a different problem, which is we are so verbose and there's so many things happening on parallel sort of streams at the same time that now you've got a different issue that you've got like all this unrelated stuff that's mixed in there. So I do think that there clearly could be a better layer of tool above this that would merge and sift and sort and like kind of dynamically grab some of this stuff. If anyone wants to write that tool, I have a ton of ideas. I have not put any of the time into it. I think you'd need it to be dynamic to be useful, because the kinds of tasks that you end up doing, some of them are like very clearly, I need to know exactly what happened at like this time point across a bunch of logs, but then sometimes if you're talking about like a timeout, you're talking about like over maybe 300 seconds, which, that distance within these logs is like 150,000 lines if you aggregate it together. So like then you also need to be able to trim and dump things as well. And
our mute friend has something to say about this.
Yes. So Matt's comment was, so a thing that you can do if it's contained within just like Nova, which does request IDs and passes them along to all the subservices, is you can actually just take that request ID, that UUID, and you can throw it in Logstash, and it will show you a time sequence of everything that got logged with it, which will jump back and forth between all the services.
Above, right?
What?
But only at info level and above.
Only at info level and above. Although the request UUID is typically not logged at debug level anyway, if I remember correctly. The context we use is different, I think, there. Yeah, there could be better tools here. If there's a volunteer, I will totally give you tons of awesome ideas.
If there's anyone out there, here's an idea. So you know how in syslog for various tools, you'll see things like this message repeated 20 times? That would be awesome to like grep out or like sort of consolidate, because the way that Tempest and the tests currently work is everything is in this status polling retry loop. And so, for instance, when you're trying to get the status of a Cinder volume or a boot instance, you'll see 20, 30, 50 different requests, and they are all identical. It would be nice if we could just say like, oh, this was repeated 20 times, with this.
The problem is they have like unique request IDs or tokens they pass to other services or whatever, so it has to be kind of a tool that knows what it's looking at, right? More than syslog does. But yeah, that would be pretty awesome.
Yeah, and that's actually I mean, I think that feeds into actually, like just a side digression before we move back on to the main topic here, is we talked about at this past summit some of the more like interesting sort of dynamic logging things that could be done within OpenStack, and actually putting that logic directly into like the Oslo logger would be really nice because like, you know, with a very small amount of internal cache, it could realize that the only things that this system is sending right now is the same thing over and over and over again, and that's not all that useful. But that's at least a like L time frame because there's a bunch of other things on people's plates on this cycle. But I do think that over time, another thing that I am that I've been pushing is sort of this log harmonization effort within OpenStack, and a lot of this has been about one of the reasons why that became important to me was reading these logs demonstrated how completely terrible it is for anyone to read any of these logs ever, and that includes all the people running real production clouds. So if we fix our problems, we fix their problems as well, and we can do that kind of iteratively, where it's like, well, this is all craziness, we should get rid of this. Or we should make it make more sense, or whatever. Okay, so it's a good point. It's another thing that love volunteers to come help with. There's many places to help in this process. So okay, if you don't find the like smoking gun of a giant stack trace that's exactly related to your problem, which honestly does happen about 20% of the time, then the question is like, okay, things are more subtle. Like, what's the next step? And the next step is to actually figure out, like, Tempest wants to do the following set of actions. Did they actually happen? Was there an error of omission? Which is one of the reasons for, again, in the logging standards about the fact that like info log messages being units of work is that we need to be able to find errors of omission where we expected a thing to happen and it did not, and that it's easier to figure that out. And sometimes we found things where, for instance, we actually log a ton of information about locking and unlocking at debug level, and sometimes you will find, if you spend the onerous amount of time sifting through, looking at a thing that got locked and unlocked and locked and unlocked and locked and unlocked, you will realize that at some point it didn't get unlocked. And the whole failure was a deadlock scenario. And that, is a thing that you can figure out there. Was there a clear point somewhere where things just like came to a halt, and is there enough to trace back on it? The last kind of bit, if like none of this works, and a lot of this, these are all very time-consuming efforts. This is building a model in your head of here's what the tests are doing, here's what the whole environment is doing, and it takes a bit of time to like kind of conceptualize this in your head of like, okay, here's this request stream, this tenant's requesting this resource, these things are supposed to happen, they seem to be happening, as we get further and further into like more pernicious issues to track down, I'm trying to boot a server. Figure out what else is happening at the same time. For instance, when we looked at the issue that we had with the libvirt live snapshot code, after like a couple of days, one of the realizations was when this failed, it always failed as another libvirt QEMU spawn was happening. It only failed if two were happening at the same time. So there was some actual lower level interaction. They were in different tenants, but there was some lower level interaction within libvirt or QEMU or something itself that if you do these two operations at a system level at the same time, we're toast. And actually, based on some other things which crept up recently, that might actually all be related to the fact that EB tables is a giant race condition. And libvirt calls EB tables, and we call EB tables, and its badness. But
Do we now have the libvirt d-logs included in the log output? I know that
we have a chunk of them at a debug level that we think we can sustain.
Okay.
Yeah, a big part of it is that we also have to deal with the fact that we have some limitations within the whole system, and is a bare metal, so it's not going to have a libvirt log, or it's going to have a very weird one.
Yeah, it's got something I just realized.
Yeah. So we have certain log retention challenges. The log stash environment is like, I think it's like, I don't actually want to remember how many terabytes it is. It's a bunch of terabytes. And it's sharded over 6 worker nodes. And the net of it is we can keep about 10 days worth of index in it. So we only really have the last 10 days to work with in the search engine. And then we are limited currently to 14 terabytes worth of log storage on our static log environment. That'll get better as we move it into Swift. That means that right now we can keep about 4 months of logs at the current output rate. And when libvirt was like turned up to all of its debugging, it was more than all the rest of the logs for the run. So it was like noticeably shortening our lifespan. So we're at some balance right now of what we think hopefully is useful.
Do we store the logs for successful runs at the same rate that we do unsuccessful runs?
Yes. We do.
Perhaps that's something we could look into not doing.
There are many things that could be looked at in the system. Again, if there's a volunteer that wants to own like optimizing the system, we can put you to work.
Sure. Sorry.
No problem. So the last thing I just wanted to say, and then we'll dive into some questions here, is that you may get to the end of this run, you may spend like, a day looking through all this stuff, like no obvious breaks, no one else has seen this issue, it doesn't show up anywhere else, like it's not clear that anything didn't happen that was supposed to happen, it's not clear there's any interactions. If you get to the point where you can't figure out what's happening, you should consider that a problem all by itself. I would say at that point, kind of take a step back, go get a cup of coffee or whatever your prospective poison is, and just say, what is the piece of information that if I had it, I might be able to figure this out? And make a patch to whatever the appropriate service is in OpenStack to create that piece of information.
And that piece of information may be Sean's personal cell phone number.
No, that would not be that. But the point being, right, like if you can't figure this out, and like if we as a community, being the people that write OpenStack, can't figure out why a thing fails in OpenStack, like no one in the world can figure this out. Like we are actually the people that know this code better than anyone else. So let's figure out how to make the code itself more debuggable when it goes wrong. That might be some extra debug tracing in particular places. It might be realizing that, that error of omission of like, well, we don't know what didn't happen because we never really logged any of the things that were supposed to happen. So we have no idea like that we had issues, and I think this was mostly addressed, but like actually not that long ago, many of the API services were not consistently logging their inbound WSGI request. So you're like, okay, I sent this request. Did the service do anything with it? You couldn't tell. It just didn't log it. Like, well, that's just crazy. Like, you got to actually, at bare minimum, know that the other side like got the request and ideally like know that it handed it off to whoever is next supposed to deal with it, right? Like, so things like that, you know, were there errors of omission that you can't figure out because we didn't say anything. And so anyway, and there's some instances of you know, patches that people have added here where it's like, okay, we know a thing went wrong, we weren't sure how or why. Here's some examples of increasing our information so that we understand what's going on. Okay, so question time, or I guess there's some comments in here too. The first thing to note, again, in the land of you want to help, one of the things that we keep track of is all of the failures. So this elastic recheck system, which categorizes these failures, we have a system that just is like self-auditing of how many things in the last 10 days have failed that we don't have any matches for, which means that it's an unknown bug. Like we don't even, like, something failed, no one even knows if it fails more than once. Our experience has been that when the overall categorization rate is like, realistically, if it's less than 85%, there very well could be like a killer bug hiding in there that we haven't, no one's done the first amount of categorization on, or like understands even is a thing that we should be looking for. So keeping that number up, helping us sort of get fingerprints and bugs registered and fixing is a good thing.
So
yeah. Yep.
The second question / comment that I put down there was about the sort of infamous RPC timeout, or really just timeout errors, and Matt had answered a little bit in there, but maybe you can also talk. It's like when you get a timeout failure, what specifically are the things that you look to in steps, right? Like, how do you check off, oh, okay, it's not the RPC layer, or it's not, you know, the API layer, or, like, what that to me has been probably the most frustrating thing. Is like I end up going down a whole bunch of wild goose chases and thinking, oh, I found the answer to it, and no, it's totally unrelated. And that's when, you know, you tend to get frustrated and click the recheck button.
Right. Sure. So the timeout issues are like good ones to bring up, because when we're running an asynchronous system, and Tempest is running against these things, and we do have to set some finite timeouts. Otherwise, it's very likely that this is sort of that error of omission. Like, a thing is never going to happen. At some point, you have to give up. Otherwise, like, life is terrible, and you just deadlock everything. So the first question, so I'm going to come out kind of outside in, because typically the first thing that people hit me up with when they're like, Tempest, you know, timed out on this test, is to try to increase the Tempest timeout. And realistically, these timeouts are really long. They are like, I think the shortest of our timeouts is over 3 minutes, and we have ones up to 10 minutes where we'll let a test run 10 minutes for operations that really should take a few seconds. At this macro level, the first thing, you know, this is one of the places where like successful runs are also important, which is to go look at how did this test run during successful runs, and did it really, like, you know, we hit it with a 3-minute timeout, but normally it completes in 4 seconds, and it always completes in less than 10 seconds in other runs that you can find. Like, clearly, we weren't naturally running into a timeout, right? Like, you'll get a hysteresis where if the timeout was actually the problem, you would see operations. If the timeout was a problem that we were sort of naturally just bell curving over, you would see operations that took, like, you know, 5 seconds less than what the timeout was. And then you're like, oh, okay. Which just we're we're mapping across the bell curve, and like a chunk of these things are going to fall off the other side. In most of the timeout cases, it means something has just completely wedged and would never complete. That's really the base case. And so, you know, now we're back into that, like, that error of omission. Like, a thing was supposed to happen. It did not happen. Now, sometimes there were these issues. So, like a good instance is some of the Nova Cinder communication, where Cinder will send back or I guess it won't send back a signal of Nova. It'll just, we ask Cinder to do a thing, and then we expect it should do it in 5 minutes, and it turns out that under some circumstances it just doesn't. Oftentimes you can keep an eye on the logs and go and like figure out, like, did a thing actually return later, right? Like, if it was ever going to return again, we failed this task, we moved on, we did other tests. You might see the request actually like do the right thing later. I think the Cinder stuff does that sometimes.
I think you're thinking of Neutron, because we poll Cinder, but we have found issues where several minutes later, after the test is long gone, you get a attempt to deliver an event, and the event says, "Oh, an instance doesn't exist because Tempest gave up, deleted it, and moved on." Right? That's an indication that something got delayed over there, hadn't broken, but.
Beyond that, I would say, like, Jay, you're right. These are always like the nastiest bugs. Part of it is how do we sort of macro level the information, like unlocking. I think we had a mailing list thread about this. It's just a matter of someone again coming up with the implementation, right? Like, the way we log information right now is we log that we took this lock with the time. And sometime later, once we actually gave it up, we log that fact. So if you do a bunch of clever grepping, you can like figure out all the time pairs and like rebuild the information you actually wanted, which is, I held a lock for more than a small number of integer seconds, which means I'm probably doing something wrong. Because if you're really taking resources and blocking everyone for that long, like, lots of things are going to start failing. Sometimes, I think some of the either Oslo lock stuff, I think today, will actually spit out that information kind of after the fact, but if it's actually deadlocked, we don't actually know that we're, stuck. So, like, a lot of this is that sort of step 6, like, add some more appropriate information into things so that we can catch this first failure. Which is not an entirely satisfying answer, but I would agree these are the class of things that are like the hardest to track down. Are there other questions? That's all our Etherpad questions. Any other questions, Jay or Dan or Matt via the sidebar? Matt is asking, how does he fix his mic? I don't know. You got to stop running, freedom-hating operating systems. Okay. Anything? I'm going to take us off the Etherpad. Anyone else want to throw out some ideas or questions here? Jay?
Well, I mean, I've actually asked the things that were most on my mind. Earlier, did we demonstrate Logstash, or we only have a minute left, so I guess that's not really something we should do now.
We brought up the URL for it. I would say that there are a bunch of other kind of interesting bits of information here. I gave a talk in Atlanta that walked through Elastic Recheck, and like the reasons that we did it and the infrastructure behind it. I'll put in the comments for when this ends up on YouTube. I'll put a link to that as well. That's also on YouTube. But yeah, Logstash is another good one. I don't know if we've got access to, or we've got good like Logstash how-to anywhere in this Etherpad yet, but that'd be a good thing to get written up as well.
Yeah, especially the thing that you said earlier about being able to put in an instance UUID or a request UUID,
Yep.
and for info level and up for a specific time period, I think would be pretty useful.
Yeah, no, absolutely. And I would actually recommend regardless, like, go play with, if you ever start looking at any of the failures, like, go spend an afternoon and play with the Logstash system, because it's actually pretty impressive what you can get out of it. And feeling comfortable with that, you can either take the logs raw and do things you want to do with the logs, grep, whatever, or you can get a bunch of the same like stuff out of Logstash, and being familiar with how that works is handy. Dan, any thoughts or questions from you? No, shaking.
I rarely fail the gate anymore. So I just don't really have these problems that you guys have. Sounds bad though.
I'm glad that you never have any of these problems. That's awesome. All right. I give one last call for questions, although we are at the top of the hour. I've got a few viewers still connected.
I'd like to just thank Matt for
all of his valuable input.
the picture of the Doberman. I think
well, hopefully for the next one, we'll get Matt's mic working and we'll get us running. Which I should say,
probably click on Matt's picture. So
I did. I have brought him to the forefront. No. So yes, just sort of parting words. Thanks, folks, for joining us today. This will be posted live on YouTube in probably about 15 minutes. The resolution will be better. You'll be able to read the Etherpad better there. The next one of these we're going to do in 2 weeks. Morgan Feinberg is going to be talking with us about the authentication flows all through OpenStack. So how it is that when you connect with Keystone or other services connect with Keystone, the authentication flows all the way through the system to understand, when things get authorized and don't, and how caching occurs and such. Because that is also a thing which, can break down, and it's a good thing to understand how that whole system works. We call it Keystone for a reason. If it doesn't work, the rest of everything falls over. Anyway, thanks everyone for joining today, and we'll be back in 2 weeks with another one of these, and we'll have future ones posted on the wiki as well. So
cheers.
Say bye, everyone. All right, catch you later.